If we look at Randall's function, it hits all the points. If we look at Alexander's function, it hits all the points also. But when we read number 2, something changed about those points. Now we know something about those points. After we read number 2 says something about these points representing a projectile flying through the air. So which one makes more sense now? Which model makes more sense? The Alexander's, which is the green one, or Randall's? Randall's. Because what goes up must come down. Kind of idea, right? I mean, like, the object, the projectile is not going to go up, come down, then start going up again. That doesn't make sense. Okay, what does make sense is Randall's models. So let's look at the different types of models. Before we look at different types of models, you guys put all the graphs on here, right? Like you copied it and you put them on there? Yeah. Okay, so here, look at number 3. In general, generally speaking, okay, don't get too specific. Generally speaking, how do we know which model to choose? Like, how did you know which model to choose for that one right there? Okay, how do we know? Tell your neighbors. Go. All right, that's enough talking. You should have said something like this. Shape of data. I suppose you could say shape of graph if you want to. Context. Context is what gave it away up here. That number 2 gave us context, and that's how we were able to choose the quadratic. And I guess the shape of data also includes like the behavior of the data, and and then context would also include like what makes sense. So those are the 2 things I'm going to say. What about all the different types of functions that we have? So I'm going to scroll up. We're going to look at number 4 through 7. These are the different types of functions that you guys have worked with before. Okay, so let's draw them. Okay, now it says what characteristics of a non-consistent linear function? What are the characteristics? So here is a consistent linear function. It goes like that. It's horizontal. It could be anywhere on this graph as long as it's horizontal. This one says non-consistent. So what does a non-consistent linear function look like? It looks like this. Or it can go like this. Doesn't really matter. It can go up, it can go down, but it's just a straight line. What about a quadratic function? A quadratic function doesn't have to look like this. It can look different than what I'm drawing. But that's the general idea, right? Can a quadratic function go downwards too?
Yes.
Yeah, it can. All right. See, you guys have worked with these before. What about a sinusoidal graph? We're working with those right now.
Swirls.
Yeah, this is the wavelengths one. And then finally, the exponential graph. Do you guys remember those? You guys remember exponentials?
Yeah.
Go like this, slowly increasing, and all of a sudden it just takes off. Okay, with your group right now, I want you guys to talk about the different characteristics of these functions. I gave you guys a picture to help you guys think of like the different characteristics about these graphs that make them, about these functions that make them different from each other. So go ahead, talk to each other. Go. All right, so for a linear function is always increasing or decreasing. It can't do both. It can only do one or the other. Decreasing. A linear function increases or decreases consistently. Like it doesn't change its steepness. Whatever steepness it is, it stays the same. So I'm going to say consistent steepness. Do you guys remember a word called common difference? Do you guys ever hear that word? Common difference. This is back in Algebra 1. You guys did sequences. Do you guys remember sequences?
No. How to do them.
Okay. A common difference is the same as a slope. It just goes, you have a rise and run, but it's the same rise and run the whole time. That's known as a common difference, or I suppose you can call it a slope. Same idea. All right, let's talk about quadratics. Quadratics are symmetrical about the axis of symmetry. Sometimes the quadratic function is centered on the y-axis, and therefore it would be symmetrical about the y-axis, and they call that an even function. Okay, quadratics are even functions when they are not shifted. Quadratics are symmetric. And they always do both. They always increase and decrease. Or they do the opposite. They go decrease then increase. So I'll just say decrease then increase, or the opposite. I'm going to be lazy. I'm just going to write opposite. All right, now what's so special about sinusoidal functions?
Periodic.
No, periodic. Periodic, that word's huge. And that word implies that you know that it repeats. It repeats itself. That's the most important part about sinusoidal functions. I'm going to call it curvy, because it is curvy. Hey, quadratic is curvy too, huh? Let's say curvy right here too. Curvy. It's not as curvy though. Did I not? Am I spelled curvy right? Yeah.
Yeah.
Oh yeah, I like you calling it U-shape. Here, let's do that right here. U-shape. Ooh, it's a parabola shape. Parabola. Okay, let's talk about exponential functions. Exponential functions are really unique. Exponential functions increase slowly and then increase dramatically. The rate of change is different than this one. Right here, the rate of change stays the same the whole time. It's increasing. But this one is also increasing, but look how different it looks. It's increasing gradually, and then all of a sudden, it increases dramatically. So I would just call this one dramatic. Or you guys would call it extra, I suppose. Just put your name on it. Dramatic, we call it extra. That's because the rate of change increases over time, and then the function starts increasing dramatically. Okay, so you asked a great question. You said, what do these look like? Here, check this out. A linear function. You guys remember mx plus b? That's it. Okay, a quadratic. That would be something like, let's call this g function. That would be x squared. And you could change that. They actually write it like this. What's that? It goes a x minus h squared plus k. Do you guys remember that?
Yes.
Okay, the h and k move up and down, left and right. We can do the same thing with this one. We can put it in point slope form, but I'm not going to do it right now. You guys know what this one looks like. Let's call this a j function. This is sine x. Or you can have cosine x. Sinusoidal functions are sine and cosine. And this one right here, the last one, let's see, let's call this the k function. No, the k, not the k, m. Okay, so this would be of x. This is like 2 raised to the x power. The 2 could be a different number. It could be like a 5 or a 10, whatever, but that's called an exponential function when the variable is in the exponent. If you want to write the exponential function all fancy, you can say a, and then let's just use a 2 for now. And then it would be x minus h up in the exponent, and then you'd say plus k at the end. So the h and k is everywhere. Okay, so that's generally, those are all your functions that you're going to be working with tonight.